Let's now see if we can take this general pattern for the total energy and massage it into some kind of a convenient general mathematical formula. If you take a close look at the structure of what we're doing, you'll notice I can write this as a general sum where I'm summing over each charge n as I bring it into the system. And when I bring charge n into the system, like I'm doing here with Q4, you'll notice I have to make sure it interacts only with charges that were already there. I only get terms for the charges that were there previously. So then there will be a second sum over all charges m whose number is less than the charge I'm bringing in currently. So Q4 summed over 1, 2, and 3. And then we have the form of these terms. It's Coulomb's constant times each of the charges divided by the distance between those two charges. Now, that kind of a sum is certainly a correct description of what's going on, but it's a little bit awkward to constantly try to remember which charge might have come in first and to always restrict our sums. So there's a kind of a more convenient way to write this sum that people often like to employ, and that is to do the following. What we'd really like to be able to do is to say, okay, I'd like to write this instead as a sum over all charges n and all charges m, but of course I have to be careful never to consider the same exact charge. If I consider the same exact charge, the distance like r44 from one charge to itself would be 0, and that's silly. The charges aren't interacting with themselves. So I'd sum over all m not equal to n of my combination, Coulomb's constant, Qn, Qm over R and M. Now if I do this, the mathematical form seems a little bit nicer. I don't have this less than thing going on, but I've actually made a classic error if I write it down this way. You'll notice that I have now actually double counted my interactions. If you see what's going on here, right, I can put a little arrows on my diagrams here to keep track of things. So when n, for instance, is 1, right, I would then have sum over all m not equal to 1. So I would already, when n equals 1, get the terms that have number 1 interacting with 2, number 1 interacting with 3, and number 1 interacting with 4. So I would get, I'll put little checks. I'll get 1 interacting with 2, 1 interacting with 3, and number 1 interacting with 4. So I will have counted these terms. When I bring in Q2, you see I again sum over all m not equal to 2. So I would then have 2 interacting with 1, 2 interacting with 3, and 2 interacting with 4. But I already had Q interacting with 1, and I'm now going to be getting it twice. I now have 2 interacting with 3, and I will have number 2 interacting with 4 along this line here. Now, as I continue on with this, Q3 then is going to interact with number 1, so there'll be a check on this line. Q3 will interact with Q2, so there'll be a check on this line. And Q3 will be interacting with Q4. Finally, Q4 will include a term for all of the other interactions, so it will be Q4 and Q1, Q4 on Q2, and Q4 interacting with Q3. Now, if you've been observing astutely what's been going on here, you'll notice that each line actually now has 2 check marks that come in whenever I was considering the nearest charge. So I've exactly counted all of these interactions 2 times too many. This whole term here is off by a factor of 2. I can account for it very nicely, though, by simply dividing my result by 2. So I need a 1/2 here. And this is the famous double counting factor. It's the correction, actually, for the double counting. So that's the double counting factor. That's the price we pay for having a much more easily organized summation. This summation, though, is very much worth having to deal with that extra factor of 1/2. Because look what I can do now. Let me look at this sum here. This factor Qn, right, is the same for each value of m, right? The sum is over all m. Qn is just a constant as far as this sum is concerned, and so I can pull Qn here out of my sum. And if I were to do that, then I get the following form. I'll have my double counting factor. I'm going to have my sum over charges n. I will have Qn. And then I'm going to have the sum over all m not equal to n. And what's going in here then is Coulomb's constant times Qm divided by r and m, the distance between m and n. Now, this is a very interesting function, right? This looks like a simple sum over all of my point charges and the distance from those point charges to my charge Qn, right? All the distances from n to m. What this really is nothing other than the potential at the location of charge Qn. So I can rewrite this then as 1/2 a sum over all charges n, the value of the charge, times the potential coming from all of those other charges at location r sub n. So this is the total potential for all charges but charge n. Now, I think you can begin to see what I'm going to want to do with something like this. Right? If I have some nice continuous charge distribution, for instance, this would be the perfect thing to rearrange into some kind of an integral. So let's go here down to our next page, and realizing that what we're calculating here, of course, is the total energy, U tot, up here. So I'm calculating now the total potential energy of any arrangement of charges. I'm finding that it equals 1/2. And now here I have the sum over all charges times their value times the potential created by all charges except for just that one. Now if I happen to be in a nice continuous case, so I have some crazy surface, something that might look like this, and I compute the potential from all the other patches, and I'm just missing one infinitesimal patch, well, in the limit that I divide this up into many tiny small patches, the potential, I'm not really missing much of my charge distribution at all, just some infinitesimal contribution, and so I could simply use the actual total potential here. So in the limit that I'm going to have my patches go to 0, so my little patches here go to 0, or I have an infinite number of them, that's the limit I'm considering. I would then have a sum over all of my charges, the tiny little charge dqn on each of my patches times the potential at the location of that patch. And that kind of a summation clearly then looks just like a Riemann sum for an integral, so that in the continuous case I would have this result: 1/2 the integral, the sum becomes the integral, v of n just becomes the potential at whatever location in space I'm considering, at location r, and then that would be multiplying my little amount of charge, dqn, which of course then just becomes dq. Kind of repair that. And once again, dq would take on different values depending upon the type of charge distribution I have. If it's an area like in my example, it'd be sigma dA. If it's a linear charge distribution, it would be lambda dL. And finally, if it were a solid charge distribution of a certain charge density, coulombs per cubic meter, in that case it would be multiplied by dV. And that then gives me the formula for the total potential energy of any continuous distribution of charges.